I think this week we had a couple of releases of interesting models. I want to discuss Gemini 1.5 by Google. And what's really exciting here is the very long context window, which opens up avenues for usage, for research. It opens new questions. It's one of those things where the milestone is in itself already pretty amazing, but it just opens up so many new avenues of research that it's worth talking about it. And I think the AI community, rightly so, is pretty excited about it. This is Not Even Wrong podcast. It's February 16, 2024. This is Krim Delco. Since the last update, we're up 5%. The market is roughly flat. For the year, we are down 12.4%. The market is up 4.9%. We're underperforming by 17.3%. Tesla has had a good day after the announcement that Elon Musk bought some shares to get his stake higher. He discussed that already. He wants to have a higher voting situation at Tesla. I think overall it's always positive when people buy. The question, of course, is how did he buy it? Did he borrow money? It's not clear. We have to do some more research. But overall, of course, if Musk decides to buy into the company to get more voting shares, that's a good sign. And given what's going on in AI in general, I think it's fair to say that Tesla has the potential to also be a lot more valuable, like many other AI companies. If you look at the space in general, if you just take a step back and ask yourself, okay, we had this two big AI revolutions. We had the supervised learning revolution that started with ImageNet in 2012, and now we have the transformer revolution, which started in 2017. The biggest beneficiary has been NVIDIA, and you can then sort of dissect the stack. You can say, okay, where else was money made? There is the front end, such as Google, Facebook. There is companies like Synopsys and Cadence. Then there is the chip manufacturers, AMD and Intel and NVIDIA. And then there is the actual, the people who build the systems that help the chip manufacturers manufacture stuff. Companies like Taiwan Semi and then ASML, Applied Materials. If you look at the last 5 years, which is typically what we use, there's a whole PhD level debate on whether you should use 5 years or 10 years or what is the time horizon. I just say, look, let's go back enough time so we have company specific issues can be sort of smoothed out. For example, if we want to compare Google, Facebook, Netflix, companies like that, you will see that if you just go back a year or two, the relative performance can be incredibly different because there has been some issues specifically with companies. But if you go back enough time, you will see that sort of the front end, like Google or Netflix or Facebook, they have similar performance. So my point of this whole exercise is to kind of look at you have certain companies that are certainly taking advantage of this AI revolution. Again, on the front end, Google, Facebook, etc. Then we have Synopsys and Cadence, which are design help tools. Then we have companies like AMAT and ASML, which help build the actual machines to design chips and to make the chips. And then we have the one specific case, which is NVIDIA. NVIDIA is the big winner. And the answer to the question why that's the case is really software, right? NVIDIA is an ASIC, a massive ASIC, if you will, that helps put together all the systems in such a way that they can be trained flexibly, and also that you can go with the change of architectures. That's the key. That's why NVIDIA is so powerful, is that if you have convolutional neural nets, let's say something like a tensor processing unit at Google or Dojo at Tesla is an accelerator that can help, but then you have a change in architecture, and then you have to rewrite all the compilers and everything for, let's say, TPU or Dojo, and it just you kind of miss the train here. versus at the NVIDIA level, the CUDA is one of the examples, but there's a lot more abstractions that help you kind of just go with the change in architectures. In our opinion, this is the main advantage of NVIDIA. Whether this is sustainable in the long run, we'll see. I think Microsoft has proven that if you have a software advantage, that can last for decades. And NVIDIA is sort of in that space right now. NVIDIA is in a sense is a Microsoft, and it's also an Intel, where you have the capability to design and produce massively complex chips, and also to have the advantage of a software, sticky software business model. So this is kind of where the relative performances live in terms of stocks. Now, where does Tesla fit here? Tesla is it's an AI company, it's a car company, it's a manufacturing company, and it's an energy company. So it has a lot of different, I think, startups that play together. Some of them very mature, some of them not so mature. We've discussed this in many episodes before. So what's important here is that we believe Tesla has certainly the potential to harness some more market value from AI. It hasn't been able to do that so far because it's not able to monetize any of the efforts. But clearly, there are certain efforts within Tesla that have proven, for example, FSD V12 is a proof of concept that you can have an end-to-end learned model that is able to navigate in a very complex environment. Today, I attended Shuren Song's presentation at Stanford. I am not discussing it specifically because I've discussed her now many times, but she is saying what people like Sergey Levin are saying, which is the self-driving car has the potential to become the first robot that is generalizable and can deliver fully end-to-end learned generalized intelligence, because it has certain features such as a unified standardized UI, for example, things along those lines. Again, this particular episode is not about that. This particular episode now is about Gemini 1.5, and it's about multimodal reasoning. So there's two things. One is a presentation at the Stanford seminar for I believe it's called something machine learning systems. So the seminar was hosted a lady from DeepMind. She was talking about multimodal reasoning. She introduced Gemini and Palmy and spoke about this. And multimodal reasoning is really, it's a very simple value proposition here. It's just, okay, we have text. How about we use other modalities? How can we even use them? Is there something to be gained? We've discussed Nurip's papers that spoke about this grounding, let's say, of embodied agents in text. So you tell, let's say, a robot, okay, you're on the floor and you have this and this around you, and this is what you can do. So the SECAM paper, which was sort of the first step into this direction, trying to ground an embodied agent so that the search space gets limited, right? And the question with these types of models then becomes, for example, can we, how do we ground an agent? Do we give it priors, or do we do it fully learned in data? And the more priors and the less data, the less generalizable it is, the more efficient it is. So those are the kinds of questions. I think what comes out in this presentation, in the multimodal reasoning presentation, is that there's still an open research question of how we actually concatenate multimodalities. Okay, do we embed them all into a massive space, sort of an encoded space, and then use masked autoencoders to learn, or do we maybe use a mixture of experts architecture, which leads me to the transition now to Gemini 1.5, which has multimodality in it. But the key advance of Gemini 1.5 is the long horizon. The long horizon means that it can simultaneously process, I think up to million tokens. And that offers one-shot learning on very large prompts. This is the key, right? There's a couple of examples. For example, they use a transcript from the Apollo 11 mission, a transcript which has, I believe, was about 500,000 tokens, if I'm correct. Think about it this way: it's a large prompt. It's a whole transcript of a mission, and you can query that prompt. You can do stuff with it. They have another example where they use a Buster Keaton movie. So this would be just images, no sound, black and white, and they can then query the movie. Show me a scene where this and this happens, and it can all be done in one shot. So there's no scene by scene concatenation or anything like that. It's one shot. Now, under the hood, we believe, we just read the sort of PR paper, not the actual research paper, but they link to the mixture of experts paper from 2017, which is, I think, a paper that came out from Google Brain in those days. So outrageously large neural networks, the sparsely gated mixture of experts layer. The paper itself kind of introduces the concept of mixture of experts. So think about it this way: you have a learnable gatekeeper, in a sense, a sort of really a gating function that operates like an operating system, where once you prompted it, it delegates tasks to certain sub-levels of the model, or certain functions that then can be executed. This is a lot more efficient, of course, than having a big sort of one big bulky model, and it helps on efficiency, computational efficiency, and it also helps on performance. So that's what they've used: some mixture of a combination of mixture of experts and transformer architecture. I don't have the exact composition. I don't know what they exactly did. They don't discuss it. But what's important here is really the result. We have a very large context length. You can see where this is going. For example, you could have a very large code base used as a prompt and then query all kinds of things. And what's also important here is that multimodality. So they show that you can input a picture and ask it, okay, given the code base where this particular sequence is generated, give me the snippets of code that actually generate this type of graph, for example. Or vice versa, you can say, look, I have these 3 graphs. One of them doesn't fit my expectations. Where in the code base was this developed? And can you please tell me why this is potentially wrong? So this has massive implications. I think Nathan Lambert also spoke about this today in his post, and he said there's a multi-billion-dollar market here in terms of software development, in terms of debugging, in terms of all kinds of things. And I want to sort of take a step back now. Some of the work I did in the last couple of months, that particularly whenever I came across DeepMind, the mixture of experts approach towards problem solving always stuck out to me. And the reason it sticks out is really because what they're trying to do, let's say with fun search and other examples, is try to take a very complex task, function search, or geometry guru, math Olympiad. I think there's a couple of papers that came out of DeepMind recently. They all tackle mathematical problems, problem solving, very complex problem solving, and what they're doing is dissecting the problem using a mixture of experts approach, which is, in my opinion, a very healthy way to deal with this type of problem, problem set in general. I think dissect it, divide and conquer, if you will. This is the approach, and this Gemini 1.5 is based on the same idea. I guess to finish this conversation, whenever we do things here at Orange Capital Partners, we eye it, we do it sort of with an eye on okay, what does this mean for us, right? In particular, are we going to get you know, embodied decision-making agent, generally intelligent? And the answer is yes. I mean, this is the path. You could imagine a robot doing the same thing, using a mixture of experts, architecture, to execute very complex tasks. Mixture of experts really is, I think, it opens the door for complexity, for solving generalizable complexity. So solving very difficult problems efficiently, because you can delegate. You can delegate the problem set to different levels within your system. I think another powerful thing here is, we've discussed this also in the past, which is the sort of operating system type nature of large language models. They have this ability, because of their semantic understanding, to act as operating systems. So, for example, we have, and I think Gemini 1.5 discusses this, imagine you have an agent, you task an agent with, I want to go to Lisbon, why don't you put together a nice 3-day trip for me, right? This is a pretty complex task, and the problem set here is, I just want to have fun. Let's say the agent understands who you are and what you're liking. So what does it do? It goes online, it searches for a flight, and then it looks for a hotel or Airbnb, and then it looks for activities, and it looks for an interesting coffee shop that you could have breakfast. So it finds a hotel next to that coffee shop. You know, I was just in Lisbon, for example, so it's you know, to me, it's important to have good coffee around me, and I don't want to have to walk 3 hours or take subways just to go to get a coffee. So why don't you get me a nice little hotel next to a really nice coffee shop? And then if that coffee shop is also in sort of a walkable area, because I like to walk around cities, so all these things can be delegated into sort of either a mixture of expert architecture or some sort of delegation type cascade model. And I think DeepMind's on that track. That's where the multimodality comes from. That's also where the long horizon sort of sits in this cascading, you know, mixture of experts approach towards complex decision-making tasks. And I guess to summarize, I want to say this Gemini 1.5 is definitely a big deal from an academic perspective, from a technological perspective, because it opens up the door for very, very complex problem-solving approaches. And the answer to complex problem-solving approaches is delegation, subdivision, and I think Gemini 1.5 is a great example of that kind of approach. The other thing is the multimodality, which is sort of a cousin of this. It's related to this problem. Multimodality means I have different modes: text, video, image, you know, sound. And I think it's still an open research question of how we actually concatenate those modalities. So do we just embed them in a massive, you know, embedding space, and then use transformer architecture, you know, mass autoencoders to just, you know, train on those embeddings and then query them? Or do we use different, what kind of architectures are, does multimodality require new architecture, or is it the same? Jan LeCun was just in the Emirates talking about something along those lines, where he is under the impression that this whole transformer architecture has its limits. Now, I think LeCun is a bit of a, you know, attention seeker, so let's take him with a grain of salt. But in general, the research question here is open. This is an open research question. Okay, how do we best, what kind of architecture is best suited for multimodality? And I think, again, today in this particular episode, I discuss on the one hand the presentation by a lady from DeepMind that talks about multimodal reasoning, and leaves that kind of as an open research question. By the way, what is some of the main use cases of multimodality is one is the beautiful use case is really the one where you draw a picture, you use it as a prompt, and you say, can you write me a piece of code that can generate this type of picture, or can you just generate this type of picture in a more fancy context with Hollywood quality? Or another thing you can do is you can show a graph and say, can you write me a piece of Python code that graphs consumer data in this way or that way? Like, you don't have to express everything in language, which I think is a very powerful tool. You can use images also as prompts in a sense, and query them. So you can in Gemini 1.5 they upload a whole Buster Keaton movie and then query the movie. Imagine you have surveillance data. Whether that's good or bad, that's a different question, but you have it, and then you query, okay, give me from today's surveillance of SFO airport, what is give me all the incidents where you think something funny happened, whether it's suspicious or not, or what's suspicious, define suspicious. I mean, use cases are enormous. So this is definitely opening up a door, in my opinion, for a very, very deep and wide use case and a lot of technological development. So again, to summarize here, Gemini 1.5 and multimodal reasonings are two very, very important milestones in the evolution of AI, and we're going to hear a lot more from them. And I think that's why we use this episode here to introduce that. And this is certainly not the last time we're going to talk about this. In our opinion, this is just the beginning, and it's going to open up many new avenues for development. Now, what does that mean for embodied decision-making agents? I believe what it means is, in particular, what it means is that we have a pathway towards a generalizable problem-solving agent that can navigate very complex environments. Thank you.